Okay, good morning, everyone. So last time we started talking about the Newton form of the interpolation polynomials. So the Newton forms is, in summary, is of this form. So P0, okay, it's just f of x1. So it will go through the point fx1, and P1 is just the linear equation. Okay, what is a line that go through x0 and x1? Sorry, it go through x1 and x2. Yeah, so if you put in x1, then go through fx1. Okay, and then P2, okay, is the parabola that go through x1, x2, and x3. Okay, and so on. So remember, we assume that yj is the data point, and it's a value of some function f at xj, and xj from 1 to 3 up to n plus 1. Okay, and we discussed how to find the coefficient a1 already. Okay, so a1 is just the slope of the line that go through x1 and x2. Yeah, and how about a2? So in order to find a2, we have to, okay, so before we find a2, we say that the name of aj, we call it a divided difference. Okay, so the divided difference with respect to the point xj, and it's denoted by f and open bracket, and we have a sequence of points here from x1 to xj plus 1. Okay, and now last time we discussed how do we find a1. Yeah, a1 is just a slope of the line that go through x1 and x2. So how do we find a2? Well, in order to find a2, so remember the pictures. So the pictures is, let me share the pictures. So the pictures look like this. So you have 3 points, x1, x2, x3. Yeah, and then you construct P2 in two ways. First, you construct P1. So it go through x1, x2. Okay, so this is your P1. So P1 is just the line that go through x1 and x2. Okay, so we know how to find the divided difference of the 2 points already. And then after that, from P1 we construct P2. So P2 is a parabola that goes through 3 points. So that's why it becomes P1 plus the divided difference over 3 points. So x1, x2, x3, and the product x minus x1, x minus x2. So remember, the product is only of the first 2 points. Yeah, x minus x1, x minus x2. So this one is you construct P2 from the left. Yeah, and then you can construct P2 from the right by starting from x3. So if I start from x3, okay, so I'll maybe start from x2. Yeah, then first I construct Q1. So this is a line that goes through x2 and x3. Okay, so this is a line Q1 that go through x2, x3. And then P2, now you construct P2 from Q1. Yeah, so this will be Q1 and then plus the divided difference, but now over x2, x3, x1. And so the product is x minus x2 and x minus x3. Okay, so you have 2 ways to construct P2. And now I have 4 equations. So 1, 2, 3, and 4, right? So now how do I get the divided difference of of f x1, x2, x3. Well, so now if I take 1 and 3, okay, so if I take 1 and 3, so what do I get? So suppose I take 1 minus 3, yeah, then I get P1 minus Q1, okay, then I got f of x1 minus f of x2, okay, so because this one, and then I have f, so f of x1, x2, f of x1 comma x2, x minus x1, right, minus f of x2, x3, x minus x2, right? So I just take P1 minus Q1, yeah. So now if I take 2 and 4, so if I take 2 and 4, okay, so I take 2 and 4, so 2, so now actually 2 minus 4, yeah, so I take 2 minus 4. Then you can see that, you know, 2 and 4, the left hand side are the same, yeah. So if I take the difference, then it just equals 0, okay, and then 2 will be like P1 minus Q1, yeah, and then I have f of plus, yeah, f of x1 comma x2 x3 x minus x1, yeah, x minus x2, okay, minus f of x2 x3 x1 x minus x2 x minus x3, okay. And you see now, well, we have P1 minus Q1 on the left here, yeah. So we have P1 minus Q1 on the right. So I can move, you know, and flip the sign. So if I move and flip the sign, then I have P1 minus Q1. Yeah, I just move this one to the left and then multiply by -1. Okay. Then I got what? I got f of x2 x3 x1 x minus x2 x minus x3 minus f of x1 comma x2 x3 x minus x1 x minus x2, okay. And now I compare this. So I label this one is 5, this one is my 5, and this one is my 6, okay. So you can see 5 and 6, yeah. So 5 and 6, the left hand side are the same, yeah, so we don't have to worry. And now we look at the right hand side. So look at the right hand side, so now I'm ignoring the constant, okay. So there's some constant here, okay, and there's some there's some terms, you know, I mean, like involving this product and x1 and this one times x2. So I just forgot about the constant, yeah. But now, so I just say that, okay, this one, okay, I just put it a bit dense, but here, yeah, I just say that, okay, I just focus on the term that have x in it. So if I have the term of x in it, yeah, then here, then I just have f of x1 comma x2 minus f x2 comma x3, yeah, plus some constant, so a bunch of constant here, Okay, the constant. So maybe just some constant. I don't want to write down, but essentially you have the constant. It's just this term, this term, this term multiply x1 and this term multiply x2. Yeah, but we just focus on the coefficient for x. Yeah, and I do the same here down here. So down here you have something for x squared. Okay, well actually the term for x squared got cancelled, right? Because you know the divided difference doesn't depend on the order of the points. Yeah, and now what is the term that has only x? Okay, so then you have only so if you multiply it out, right? So you have f of x2, x3, x1, yeah, and then you multiply it out, so you have x squared here minus x2 plus x3 x, yeah, plus x2 x3. Okay, and minus, okay, so f of x1 comma x2 x3 x squared minus x1 plus x2 x plus x1 x2, right? Okay, yeah, you got it, right? Okay, so now I just make a bit longer calculation, but essentially I just follow the line before. So if you see that, okay, so the line before right here, yeah. So if you see that the x squared got cancelled, then there's no more x squared here because this coefficient is the same. Remember, just a coefficient from P2. Then what you have is only f of x2, x3, x1 minus, well, minus here, yeah. Then you have x2 plus x3, x, yeah, plus some constant. Okay, so some constant. So I write x2, x3, f of x2, x3, x1. Okay, but you see the constant there. So it's just this one, just a constant. And then what is the extra term? So that the next term will be plus f of x1, x2, x3. Yeah, so remember the x squared got cancelled. So now you have, so I have a x1 plus x2 x, okay, and plus some constant. So this is another constant. So x1, x2, f of x1, x2, x3. Okay. And so now one more cancellation. So you see x2 here and x here. Yeah. So you see x2 here and x here. So this term will get cancelled, and then you can rewrite in a nicer way. Yeah. So this one is a bit dense here, but you see that you can rewrite this as f of x1, x2, x3. So remember this coefficient are the same, right? So you can make it a common term, and then you have x2 got cancelled. You have x1 minus x3 multiplied by x, and now just a bunch of constant. Okay. So you see now we look at the very last one. Look at the very last one, yeah. Okay, so this one come from equation 6 I had before. Okay, and remember we have similar situation in 5, yeah. But in 5, you know, look at the you look at this term, yeah. So you have something for x plus some constant as well. So now because p1 minus q1 are the same polynomial, so the coefficient for x have to be identical. Okay, so then you make a conclusion. So you make a conclusion that the red box after 5 is the same as the red box after 6, yeah. Okay, so the coefficient, at least the coefficient. So therefore you have, you have f of x1 comma x2 x3 x1 minus x3 equal f x1 comma x2 minus f x2 x3. And so this one gives you the formula for computing the divided difference over 3 points. So this one gives you the formula for divided difference over 3 points, x1, x2, and x3. Okay, so this is the final formula. So for 2 point, it's easy, right? So 2 point is just a slope of the line. But for 3 point, we have to consider the polynomial, the parabola in 2 ways. Yeah, you construct from the left, x1, x2, x3, or you construct from the right, yeah, x2, x3, then x1, and then you do some algebra. And then you make the coefficient of x are the same. And then this one gives you the last formula. So the last formula is the divided difference over 3 points. Okay. So I just explained the way to get the divided difference over 3 points. Yeah. So you see that in the slide, it was written in a shortened form. Yeah. So here 5 and 6. Yeah, you get 5 and 6, and then we equate the coefficient for x, and then you got f divided difference of x1, x2, x3. Okay. And now, if you replace x1, x2, x3 by other 3 points, xj, xj plus 1, xj plus 2, then you can repeat the process and you get the same formula. Okay, so you replace x1 by xj and x2 by xj plus 1 and x3 by xj plus 2, and you got the same formula here. Okay. So now you use the same method. Okay. So now if you consider the cubic instead of parabola, yeah, instead of the quadratic, then you can derive this formula over 4 points. Divided difference over 4 points, 1, 2, 3, 4. So we skip it. And then you can use induction to do further. Okay, so you can up to k plus 1 points. Yeah. And now, actually, the formula look a bit complicated, but in practice, it's very easy to compute the divided difference table. I will show you the example. So first, you make a column, x1, x2, x3, x4. And then the second column is f of x1, f of x2, f of x3, f of x4. And you see this divided difference over 2 points, you just take fx2 minus fx1 over x2 minus x1, and so on. So f x2, x3 is just to take fx3 minus fx2 divided by x3 minus x2, okay? And for this number, so the divided difference over x1, x2, x3, you just take the difference, okay, of x2, x3 minus the divided difference over x1, x2, and over x3 minus x1, okay, and then so on. So maybe it's a bit more instructive if we do the table. So you see now, so maybe forget this number a little bit, and now we do it on a piece of paper, and I show you how it is done. Yeah. So now the theory is a bit complicated, but in practice, it's very simple to construct a table. So now suppose I have x and y, okay? And then x is just 0, 1, 2, 3. Yeah. And y is 2, 0, minus 3, and 5. Okay. Now, in order to find the dividend difference here, yeah, then this one is I just take this number 2 minus 0, 2 minus 0 divided by 0 minus 1. So divided by this number. Sorry, the difference between this number and this number. Okay. So this one gives me minus 2. Okay. And then for this number, so I have minus 3 minus 0, yeah, divided by 2 minus 1. So 2, sorry, not 2 minus 1, 0. So if I take, sorry, yeah, 2 minus 1, yeah, because I take minus 3 minus 0, so then I have to take 2 minus 1, yeah. Okay. So then I have minus 3. Yeah. And then similarly for this number, I have 5 minus 3 over 3 minus 2. Okay, then I got 8. Yeah. And then I do the next. So the next one is I take minus 3 minus 2. Yeah, so become plus 2. And divided. Okay, so now it's a bit tricky here. So but now you have to divide, you have to take 2 minus 0. Okay, so you have to take 2 minus 0. So this one gives you minus 1/2. Okay, and you do the same here. So this one is a minus 3, so become plus 3. Yeah, divided by, so now you have to take 3 minus 1. So 3 minus 1, 3 minus 1. So this one gives you 11 over 2. Okay. And the last number, so the last number is you just take the difference here. So 11 over 2 plus 1/2 divided by, so 3 minus 0. Okay, so 3 minus 0. So then this one gives you just 12 over 2 is 6. 6 divided by 3 is 2. So this one is 2. And the last one. So now the now you look at the number here. Okay, so those numbers will give you the Newton form of the interpolation. Yeah, so now I will write P3. So P3 is the cubic that interpolate the data, and now it will be equal to, so 2, the number 2 come from here. Okay, so 2 come from here, and then minus 2, so minus 2 come from here. X, okay, X is just X minus, so X is just the very first factor, and then after that you have minus a half, so minus a half come from here, so then X minus 1. Okay, and the last term is 2, so 2 come from here. Yeah, then x minus 1, x minus 2, and then you can verify that this one is the interpolation polynomial. Well, I mean, you can check. Yeah, so now if I put in x equals 0, so P3 at 0, then everything here just gives you 0. Yeah, so then you just have 2, and then P3 at 1. Yeah, then you have this one is 2 minus 2, right? And then the rest are equal 0, just equal 0. And then you do the same P3 at 2 is P3 at 2 is just well, you put in 2 here, so 2 goes away here. So you got 2 minus 4 plus, minus 2 over 2 and 1, so will be 2 minus 4 will be minus 2, so minus 1, so minus 3. Okay, and so on. So then you have P3 at 3. Yeah, you just put everything in. Yeah, so then 2 minus 3 multiplied by 2. So let's put it in. And you will see that it will give you the correct results, 5. Yeah. So you see, like both methods, you know, the Lagrange method and the Newton method, both methods, you don't have to solve any linear system. Okay. And so Lagrangian is you have to give a Lagrange polynomial. And this Newton method, you just have to compute the divided difference table. So this is the divided difference table we computed. Okay. You can do it by hand, or I wrote a MATLAB script to compute it for you. And then once you got the data, once you got the coefficients, then you can construct the Newton interpolation polynomial. Okay, so no need to solve any linear system. And you see now, suppose you have a new data. So now suppose x equals 0, 1, 2, and 3. So tomorrow I woke up and I got x equals 4, y equals 6. Then I just, add on some more coefficient. Then I just write down another polynomial. Okay. So this one, you don't have to do all the polynomials again like Lagrangian. You just add on a new polynomials. Okay. So here, this is the simple MATLAB program to compute the divided difference table. Yeah. So you just understand what is going on, but now you can write a MATLAB program to compute the divided difference table. So now how do we use this? So how do we use this? You see, so this one, I just implement exactly the algorithm before. See, T is a table, right? Yeah. So T is a table of n rows, n plus 1 columns. Remember, we have n plus 1 points, yeah? And we label from 1 to n plus 1. So the first column is is just X, yeah. And the second column is just the Y, yeah. Okay. And now, so this one is from the third column. So J is the third column to the final column, yeah, the n plus 1. Then what I'm going to do, so I'm going to set I to be on the rows from 1 to n minus j plus 2. Okay. And so this one is just my formula for divided difference. Okay, so I have, so on the denominator is just the difference in the data points, yeah, in the xj, yeah. So this one, remember the first column is the x, yeah, and you have to take x the correct points, yeah. And now what is the output? So if you run it, what is the output? What does it look like? So what does it look like? So it look like this. Okay. So suppose I put in x data. So let me see whether any question. So any questions so far? No question. So if you put in the data, right? So here is from 0, 1, 2, and 3. And the y data is 2, 0, minus 3, 4. Okay. Then how do you extract the coefficient? So the output will look like this. So how do you extract the coefficient? So now I say that, okay, how do you write the polynomial in the Newton form based on these results? So where do you get the coefficients? Anyone? Are you still there? First row of the table, yes, correct, yeah. So the first row of the table is, you see now 2 here, right? Then minus 2, yeah. So minus 2, and then minus a half here, yeah, and then 2. See, because you know, like if you do it by hand, then it's very easy to make a rectangle, I mean a rectangular matrix like this, yeah. But from MATLAB, it's not obvious, yeah. So then we move, you know, the minus 2 here up, minus a half here up, 2 here up to the very first row, and that's why, you know, we have the structure like this, yeah. So this is still the divided difference table, but you push up, so it's become like upper triangular like this, and that's explain why you got this index calculation, so you can verify this is the correct way to do it. Okay. And so this file dd, I put it in Moodle as well, so it's a function, and it's very straightforward from the algorithm to compute the divided difference table. Okay. And now, so this one is just another example. So we have a different data set, yeah. And then we use the cubic to estimate what is f at 1.3. So first you construct a line, yeah. So this one uses a linear. So what is a line or cubic? So for a line, it's easy. For a line, you can write out the equation. But for the cubic, then you have to compute the divided difference table. So this one you can put into MATLAB. Okay, put the x here and the y value here. You get the coefficient and you form the polynomial. And then you can see that if you put in the value x equal 1.3, then you get the approximate value of the function f and 1.3. Okay, so the interpolation errors is just the difference between the polynomials and the function at that point. So in this case, you know, the cubic give you about 10 to the minus 5 errors, but the linear interpolation give you bigger errors. Yeah, you can test it. So there will be some question in the labs, you know, next week, like for you to compute the divide difference table and the interpolation polynomial. And so now in other situation, you can have what we call a Hermite polynomials. So Hermite polynomials is like, you know, the values of the point, but then you know the derivatives at the point as well. Okay, so pj, so j here is just the derivative. Okay, and you know, I mean, maybe this one is, we just say that we are not going to do it in details, you know, but I just give you an example. So suppose that you find a polynomial p, okay, that satisfy this condition. So p0 equals 0, p1 equal 1, and p prime. So this is a derivative, p prime 1 equal 2. And how do you find it? How do you find this polynomial? So what is the degree of this polynomial? So we have three conditions. Yes, so it's a 2, right? Because degree 2, because you have three conditions, yeah? So you have three unknowns. So if you have a line, you have a linear, then you have two unknowns, but you should have three unknowns. So it's a polynomial degree 2, so it's a quadratic, yeah? And you can do this by you know, like by writing a linear system. And so this one we can assume that so p is ax squared plus bx plus c, right? And then you have three conditions. So p0 equals 0, and p1 equal 1, and p prime at 1 equal 2, right? So then you have three conditions. So at x equals 0, you just have c equals 0, yeah? So easy, right? And x equal 1, you have a plus b plus c equal 1, yeah? And derivative, so now 2ax, okay? And then you put x equal 1 plus b, okay, equal 2. So you have c equals 0, so you just have a plus b equal 1 to a plus b equal 2, yeah? So this two system, and you take the difference, and you got a equal 1 and b equal 0. Okay, so we can solve three equations like this, you know, easily, yeah? So we will stop this topic, at least for now. But you see, now there's a special case when you have only one point, then then what is this special case? So what does it mean? So suppose you have a polynomial p, yeah, say at 0, and you know the value p0, and you know p prime at p0, and you know p double prime at p0, and p triple prime at p0, and so on. Then what is that? What is that situation? So what is the situation? So if you have, yes, so it's a Taylor polynomial. It's correct. It's very good. So you're still paying attention. Yes. So if you have only derivative at one point, then essentially this is a Taylor polynomial. Okay, so you've seen it before, right? So it's very good. Okay, so you're still awake. Yeah. So now we will not discuss this type of interpolation further. So now the next topic I want to say is what is the errors? So the errors is the difference between the exact function and the polynomial you try to interpolate. Yeah. So remember you have interpolation condition at the point, at the data point only, you know, x1 up to xn plus 1. But what happened at other points? So that is the question. So what happened at other points? So suppose you have x, okay, is another point not the same as the data point. Then you can define the errors so that the errors will be a function depends on x. Yeah, you put in f of x and you put in Pn of x. So Pn is your polynomial, the interpolation polynomials. You take the difference. And you want to find out what is the errors, how big the errors can be. Okay, so essentially, if x is the interpolation point, then this error is just equal 0, right? And now, before I want to say the errors, let we define some notation. So we say that f in CR, okay, if f, the first derivative of f, the second derivative of f, up to the r derivative of f exists and continuous. Okay, then we say that f is in CR. So r equal 1, then you have f and f prime exists and are continuous. R equal 2, then you have f prime, the second derivative exists and continuous, and so on. And now the theorem say that, okay, so the errors can be given explicitly like this. Yeah, so the theorem say that if f is n plus 1 differentiable, I mean continuous and differentiable, yeah, on the interval started at x1 and ends at the last data point, then you can write down the error function enx as this explicitly formula. Okay, so xi is some point in the interval x1, xn plus 1. And this one is just a derivative of order n plus 1 evaluated at xi. And this one is just n plus 1 factorials. And this one is a product x minus x1. No, that's a good question. But you see, that is our assumption. So we have to assume that it's differentiable. Okay. And then it implies that it's continuous. Okay. So because if it's continuous, then it's not automatically differentiable. Okay. So but we assume that it's differentiable first. So therefore it's continuous. Okay. So now how do we prove this? So now this theorem is very interesting. So how do we prove this? So we can prove this by in 2 steps. Okay. So the first step is we have to prove the mean value theorem for divided difference. So what is the mean value theorem for divided difference? So the mean value theorem for divided difference saying that suppose you have x1 less than x2 less than xn plus 1. Yeah. And f is Cn. So which means that the nth derivative of f exists. Then the divided difference over x1 up to xn plus 1 can be written as the derivative of order n some point xi over n factorial. Okay, so we look at this theorem first, yeah. So suppose I share my piece of paper. So now the theorem saying that like this. So f, well, so we just assume that f is very nice. So everything very nice here. So then you have f of n xi over n factorial. So how do we prove this? So now maybe let me take a very simple case. Okay, so before we try to prove it, see whether it's true or not. Because if it's not true, then what is the point trying to prove it? So suppose I take n equal 1. Yeah. Then I got I got f x1 comma x2 equal f prime xi over 1 factorial. Yeah. So what is the divided difference over 2 points? Well, it's just f of x1 minus f of x2 divided by x1 minus x2 equal f prime of psi. Yeah. So what is this theorem? So anyone? So anyone recognize this theorem? Is the yes, it's the mean value theorem. Yes, you recognize it. So the mean value theorem it's just this special case. So it's correct, right? So n equal 1 is correct. Yeah. Okay. So it's just a normal mean value theorem. So it's correct. N equal 1 is correct. So that's why, you know, it has the name, the mean value theorem for divided difference. Yeah. But now how about n equal 2? So now how about n equal 2? So n equal 2, then that's become tricky. So I have f of x1, x2, x3 equal f double prime over 2. Okay, so how do I prove this? How do I prove this? So this one doesn't have any formula before, right? So now maybe we have to do something like this. Okay, so now suppose I define a polynomial p. So I define polynomial p, yeah. So p which has this property. So I have a, in this case, I assume that p is interpolating f and x1, x2, x3. So I want p x1 equal f of x1 okay, and p x2 equal f of x2 and p of x3 equal f of x3. I have only 3 points, so yeah. So then what is p? So p is just a parabola, right? Yeah, but then what is p in terms of a Newton form? So remember you have p, yeah, can be written as f of x1. So now we use the knowledge of the Newton form, okay? Plus the divided difference x1 comma x2 x minus x1, yeah, plus f x1 comma x2 x3 x minus x1 x minus x2. Okay, so far so good, yeah. Okay, so now let me introduce another function. Maybe I call it function g, yeah. So function g will equal f minus p. Okay, so now what's so special about this function g? Well, I know that g at x1 will equal 0. Yeah. Why is that? Why g of x1 equals 0? And not only gx1 equals 0, but gx2 equals 0 as well. And gx3 equals 0 as well. So why is that?
px3 equal to function x3.
Sorry?
px3 equal to function x3.
Yeah, because f at xp and p at xp are the same, right? For x1, x2, x3, yeah? So therefore, I have this property, okay? And now if I draw it, so I draw my function g. So it looks like this. So this one is the line OX, yeah? And now this one is x1, x2, x3, yeah? Then my function g look like this. I mean, I don't care what value, but I know that at x1, x2, x3, it has to be equal to 0. Okay? And now there's a theorem saying that, so if, you know, g x1 equal 0 and x2 equals 0, then there's a point in the middle. Okay, so I call this one is, say, y1, yeah, and somewhere in the middle, this one is, we call it y2. Okay, so there's a theorem say that there exists y1 in yeah, so this one is a notation in x1 x2 in that interval, and y2 and x2 x3, so that g prime y1 equal g prime at y2 equals 0. Okay, so you know this theorem. So I think there's a theorem called Rolle's theorem. Yeah. So by a French guy. So Rolle's theorem. It just say that, okay, if it equals 0, or just as a consequence of mean value theorem, but apply for g. Yeah. So there is a point in the middle here. Okay. So Rolle theorem or mean value theorem again. Yeah. So to say that if this equals 0 at the two ends, then there is a point in the middle, so that the slope here equals 0. Yeah. So you can label. So this one, suppose I have, so g1 to be g prime. Okay. And now g1 at y1 equal g1 at y2. So therefore, there is a point, say Z1. So that G1 prime at Z1 equals 0. Okay. And what happened at G1 prime is just G double prime. So G double prime Z1 equals 0. And now I stop here. So I stop here, yeah. So what is my G double prime? So G double prime at Z1. So this one again is a wrong theorem again, yeah. Or mean value theorem in a special case, yeah. So what is G double prime? So G double prime is just F double prime at Z1 minus P double prime at Z1. And you know that F double prime we just still have here, yeah. But when you take the second derivative of a parabola, right, then you just have 2 factorial times the first coefficient, which is x1, x2, x3 equals 0. And this is exactly what you want, right? So this one is exactly what you want. So you just have f of x1 comma x2 x3 equal f double prime at z1 divided by 2. That is what we just proved for the case n equals 2. Okay. So any question? And we just proved the case for n equals 2.